All right, everyone, we're going to learn about confidence intervals for the means of large samples. Our learning objectives are to review the distribution of the sample mean for large samples, meaning sample size is typically greater than 30. And this distribution arises from the central limit theorem. We'll then apply that distribution for sample means, which is, hint, the normal distribution, to define and construct confidence intervals for sample means of large samples. All right, so since this is civil engineering and some of you may be taking geotech right now, let's think about a series of unbiased measurements that you're taking. So series of unbiased, meaning we're assuming that our method isn't biased. And we're also assuming that they are independent measurements, meaning there's no trend or correlation between one and the other. And we're also assuming that these are kind of random samples. So there's some sort of random sampling scheme here as well. We'll take somewhere around 30 or maybe more samples. And speaking of geotech, the example we'll talk about today is permeability. So we're going to think about measuring the permeability of soil. In geotech, it's called permeability. In hydrology, we call it hydraulic conductivity. So this K value, which has units of length per time. So you're taking your measurements, you're looking at how water is flowing through this porous medium and estimating this K value. So say you did this, you took some measurements and we pooled all the measurements for the class together for the same soil type. And we found the mean of that sample. And let's just say that that mean was 0.055 centimeters per day. And then you went and calculated the standard error, so S over square root of 30, or N, and that was 0.002 centimeters per day. All right, so we could estimate our uncertainty as our X bar plus or minus our standard error, or 0.055 plus or minus 0.002 centimeters per day. So we could say that's our best estimate of the mean value with some uncertainty that we've estimated. So that's good, that's helpful. But how confident are we that our mean our sample mean, X bar, is close to the true mean, the population mean mu? That real hydraulic conductivity that for that particular soil under that particular setup. Well, our uncertainty just gives us our uncertainty estimate of the mean itself, the sample mean, but we're interested now understanding probabilistically how close are we to that true mean. So our question now is, what is our confidence that our sample mean approximates the true mean value here? Well, we know that from the central limit theorem, that if we take any random variable, and we take the mean of that, so we take a sample from any random variable, we calculate the mean value. That mean value will follow a normal distribution with some mean X bar and some standard deviation X bar, which is S over square root of N. So that's arises from the central limit theorem. It doesn't matter what the underlying population random variable distribution is, the means of those, given a large enough sample that n is greater than 30, should follow a normal distribution. And so let's just say we went back to that permeability lab and ran it 1,000 times. That's your job, to really figure out the permeability of this soil. And so you take 1,000 samples. And each time you calculate a sample mean. So sample mean 1, sample mean 2, all the way to 1,000. Sample mean 1,000. Okay. Those sample means will follow normal distribution. All of those. So we'll have a distribution. It'll be centered around, ideally, assuming that we're unbiased, the true value of mean. And we'll have this normal distribution for our sample means. So now we can start thinking about, well, within this distribution, and I'm going to draw this a little bit bigger, hang on. Within this distribution of sample means, we know from the empirical rule for the normal distribution that if we go out 1 standard deviation from the true population mean, so 1 sigma, in either way, that we're going to capture about 67% of the probability within here, so 0.67. If we go 2 standard deviations out, let's take a look at that. Then we're going to get about 0.95. And so on and so forth. We can go 3 standard deviations out, and that's 0.997. So we can say something like 95% of the sample means should fall within 2 standard deviations of the true population mean. If we think about each sample mean as being something that can fall, we could have sample mean 1 here, we could have sample mean 2 here, sample mean 3 here. They're all over the place, right? Some of them might be far away. Sample mean 976 could be way over here. But we should say on average, most of these fall within some standard deviations. If we could say 95% of them fall within 2 standard deviations of the sample mean. So this is starting to help us get towards a confidence interval here. So what in fact a confidence interval is we want to state what our confidence level is. So confidence interval or CI, I'll refer to it as CI from here out. So we want to state confidence level and say that's 95%. We'll just kind of stick with that. So we have a 95% confidence. And then we're going to use the normal distribution to calculate the confidence interval based on that confidence level. And hint, hint, if we say it's 0.95, then we're going to be using some sort of z-score to get us out to that point. So we'll look at that on the next slide. So to construct the confidence interval, we will think about the following. If we want to say we have a 95% confidence level, we need to find the z value that, or the z values, let's say, that span the middle 95% probability centered around that mean value. All right, so if it's 95%, then we want, let's say over here, we want z, whatever that lower is, we'll just say z lower, and then we want z upper. And in the middle, we want 0.95. for that area within that. So to get that 0.95, if we were to say, okay, well, what's the probability up to this point that gives us 0.95? Well, we're going to be kind of double counting the tails over here. So we have to subtract these tails. So if the area in both these tails is 0.05, which we'll call alpha, and I'll talk about alpha in a minute, this is going to be alpha over 2, and this is going to be alpha over 2 for the area. And so alpha in this case, or alpha over 2 in this case, is going to be 0.025, and this will be 0.025. So those two will add up to 0.05. We subtract that from 1, and in the middle we get 0.95. So we need for z lower to be z alpha over 2, and z upper is going to be 1 minus alpha over 2. And for alpha over 2 being 0.025, this is going to be the z associated with 0.025 of cumulative area. And this is going to be z associated with 0.975. So not super intuitive at first. You're like, why am I not calculating z 0.95? Well, we have to subtract out the two areas, and we want it to be centered. So we're going to then go to our z tables, or we could go in Python and just say norm CDF, if that's the function, if I'm thinking of it correctly. We give it the location, which will be x bar. We'll give it the scale, which will be s over square root of n. And then we'll give it the p-value, which I think is the first one you give it. But anyway, so actually, no, we want norm ppf. Sorry, we'll get back to that. More Python later. Sorry, I can't do Python off the cuff. All right. So let's take a look at our z table right here. And let's find the values that we need for z. So it's symmetrical. We need to find a z value associated with, on this side, we're on the negative side, 0.025. That's 0.0025, so let's find 0.25. And we are right there. Okay, so that's going to be negative 1.96. So that's the value we want. So z alpha over 2, z 0.025 is equal to negative 1.96, and z 0.975 is equal to 1.96. All right. So that gets us our interval. And so now to, our z values to help us with those intervals. So now to construct the interval, we're going to start with x bar. And then we're going to go plus or minus z alpha over 2 s times s over square root of n. So that's our sigma value, right? That's just sigma x bar. So now we're saying, okay, we're going to go out this way. It's almost 2. It's not quite 2, right? It's the empirical rule's not super precise, but at a more precise level, we get 1.96. And then we multiply it by our sigma, which is just s over square root of n. So to do this, we'll do the actual value, which is 0 for permeability, right? 0.055. And then we'll go on this side, we'll do 1.96 times 0.002. That was our s over square root of n. And then on this side, we'll have, so this will be 0.055 plus, and then this will be 0.055 minus 1.96 times 0.002. Okay, so if we run that calculation, we end up with 0.055, which is going to be centered on within 0.059 and 0.051. So that is our 95% confidence interval for X bar. All right, good job, everyone. So let's talk a little bit more about alpha. So we said that alpha is the whatever we're not confident in, right? So if we want a 95% confidence interval, we're saying that 0.05 of that is not confidence. What we're saying that is, okay, if we draw that 95% confidence interval around this mean value right here from our sample. So we go over here, we go over here, that's our confidence interval. What we're saying is that 95% of the time, and this is kind of one of the definitions of a confidence interval, 95% of the time, the confidence interval about the sample mean, X bar, will contain the true population mean, mu. And it's really a probabilistic thing. So I take one sample, I do a confidence interval, one sample mean confidence interval, it covers the mean. I do another one, it covers the mean. I do another one, it covers the mean. If I do it 100 times on average, then 5 of those won't cover the mean. In fact, my confidence interval won't in fact reflect, or at a 95% confidence, not actually encompass the mean. And so this is what we call a type 1 error, which is basically the probability that we should say it covers the mean based on, what the sample is, what the mean is, what the standard deviation is. But in fact, this particular sample happened to be pretty high or pretty low. And so we actually didn't cover the mean. You'll never know what that is or if that's true, but from a probabilistic standpoint, that's what that alpha represents. It's just the probability that your confidence interval doesn't cover the mean when it should, when your sample is from this population mean. So let's just take a minute to look at what this looks like in kind of a simulation standpoint. So what we have here is a simulation that is taking random samples. The blue dots are the mean values, and then the bars are the confidence intervals. So 95% confidence interval. And the sample mean is represented here in the center. And what it's showing is that if we take hundreds or even thousands of samples, on average, that percentage of those should be 95 that confidence interval actually covers the sample mean. And so this has been running for a little while. We've got about 160 going on 200 samples that we've taken. And here's tracking over time the proportion of samples that include the population mean. So under the simulation, we're right at about 95%, 95.4%. Now I can speed this up and kind of crank it up and go a little faster. I can increase my sample size, and that is going to reduce, as my sample size goes up, my confidence interval reduces because we're dividing by square root of n. So that's good to know. Then I can also reduce the confidence interval. So I can go down to say let's just do a 90% confidence interval. And what this means is that, well, my confidence interval is going to be shorter or narrower because I don't have such a big Z value, and we'll do that in a sec. So I should only expect about 90% of them to incorporate the true mean value. So you can see I'm getting some more red ones over here on average. But then I get a smaller band. So I have kind of more precision here, but a little bit less reliability. So let's talk about precision and reliability here. We'll come back and see how we go, but our new bar is 90%, and we're kind of cruising. I think we're going to get there pretty soon, coming back up to 90% asymptotically. So you can see that some of our confidence intervals still don't incorporate the true sample mean. About 90% of them do. So let's talk about reliability versus precision. Reliability gets to accuracy, or how, or confidence, right? How confident or how reliable is our confidence interval in covering the true population mean mu, right? And then we have precision, which is the width of our confidence interval. A wider confidence interval is less precise, a narrow confidence interval is more precise. We can say, okay, there's just kind of less uncertainty here. But then as we narrow our confidence bands, say we come out to here for a 90%, then we're less likely to actually incorporate the true mean mu, and our alpha increases, right? So for a 90% CI, alpha is 10%. And so now we get a greater probability that we don't in fact cover that true population mean. So important to know. Now on your own, I want you to do a calculation. On your own, I want you to calculate the 68%, 90%, and 99.7% confidence interval for our sample mean. And remember that sample mean was 0.055, and then our standard error was 0.002 for permeability. So pause here and go ahead and calculate that. I'll give you the generic formula where we have X bar plus or minus Z alpha over 2 S over square root of n. So times S over square root of n. And then alpha is going to be equal to 1 minus confidence level as a fraction or decimal. So let's do this together. We'll start with 68% confidence interval. And to do that, we need to first define our alpha. So in this case, alpha is going to be equal to 1 minus our confidence level, which is 1 minus 0.68. And that's going to be 0.32. Now to get the Z values, we need to divide that alpha by 2. So alpha over 2 is 0.16. And then I've got a different Z table over here, but we'll figure it out together. So that would be the lower Z value would be the cumulative area under the tail would be 0.16. This would be alpha over 2 is equal to 0.16. But then we need to find the upper Z value since I've got the upper table here. So 1 minus alpha over 2 is going to be equal to 0.84. So that's that upper Z value. So Z 0.84. Let's find that on our table. Getting pretty close. That's about it right there. So that's going to be 0.99. So right around 1, right? From the empirical rule, 68% is 1 standard deviation. So we'll just say for all intents and purposes, it's 1. And now to construct our confidence interval, we're going to be saying X bar plus or minus 1, which is our Z value, times 0.002, our S over square root of n. And so our 67% confidence interval will simply be 0.053 and 0.057. Okay. Now, I want you all to do the others. So pause this and go ahead and calculate the 90% and the 99.7% CI. So for our 90% confidence interval, we've got plus or minus z value of 0.164. So that's the approximate for our alpha over 2, which is going to be 0.05 and 0.95 on either end. So that gives us the 1.64 from this table. And then we'll multiply that point by our standard error, and then we add and subtract it from the sample mean. So that gives us a confidence interval of 0.052 and 0.058. Okay, and then we'll show the 99.7% confidence interval in just 1 second. So now that we've calculated the 99.7% confidence interval, we can see that it's a little bit wider. Our alpha is 0.003. Remember, we have to write this out as a fraction. So 1 minus 0.997 is 0.003 divided by 2, we get 0.0015. And then we find our z-scores associated with that. So the upper one is going to be 0.9985. So that gives us a 2.97 z-score. And then we multiply that by our standard error, add and subtract from the sample mean, and then we get our 99.7% confidence interval. So let's just review. We had first our, let's see here, X bar. We had our 67% or 68% confidence interval. And then we calculated a bigger one that was our 90% confidence interval. And then as we keep going in confidence, our confidence increases, our reliability increases. But you can see the interval is getting a lot larger. And so that was our 99.7% confidence interval. So as our confidence increases, also known as reliability, so does the interval. But of course, we get less precision. So that's just the way it goes. All right, one other point I want to make is related to confidence and probability. So probability versus confidence. When we make an interval like we just did that has these bounds, this was 0.055, and then I think our 95% was something like this. That was our 95% CI approximately. When we write that confidence interval down and calculate it, all we can say is that we have 95% confidence that interval encompasses the true mean. From a probabilistic standpoint, but that's not a probability. It's not that there's a 95% chance that the true mean is in it. We just have 95% confidence. When you get to probability statements, you can say that there's a 95% probability that the following confidence interval covers or encompasses the true mean value. And that's more of a kind of like sample design perspective, where if I were to do 1,000 of these, like that web example that we'll look at in a second again, on average, 95% of those confidence intervals across many sample means, many samples, will encompass the true mean. So I just wanted to draw that distinction. When we calculate a confidence interval, we're saying we have 95% confidence that it encompasses the true mean with that type 1 error of alpha. which is just 1 minus our confidence level. And then when we think about the definition of a confidence interval, there's a 95% probability that it encompasses the sample mean over many confidence intervals that we might do. Let's look at some of our assumptions. We said up front that these confidence intervals apply to random variables that are independent, or random samples that are independent. So here's some examples that are not random or independent. And we see a periodic trend here on the left where sometimes they're high and sometimes they're low, but there's a period to it. It's not just a scatter. And so you can see that when you take your sample, depending on where you are in time, maybe it's like during warm time of the day and cool time of the day, you're going to get a different answer. So that's not going to be a random sample. On the right, we see a trend where it's increasing over time. Again, not a random sample. It doesn't reflect kind of a static mean and standard deviation over time. So that's important to think about when we're calculating means of samples and confidence intervals and comparing them. All right, let's do one more example for this lecture. So we just calculated a confidence interval for a large sample. Now let's kind of inverse that and calculate the sample size that we need to take for a given confidence level and interval. So in this case, we have, we're going to go to Enstrom's Toffee here in town, and they sell a nice almond toffee, chocolate covered 12-ounce box. So the mean value is just a little bit over 12 ounces of the weight of the toffee that they put in there. And here is the standard deviation, not standard error in ounces. Butter's not cheap, guys. Inflation, it's going up. We got to really tighten our belts here and make sure we get some better tolerances. So we want to do a better sample size and calculate a tighter confidence interval. So we want to find the necessary sample size n to achieve a 99% confidence interval for the mean, given this standard deviation. So let's figure this out. We've got our confidence level is equal to 0.99. So 1 minus alpha is 0.99, and then alpha is 0.01. And then z 0.005, right? So alpha over 2 is equal to 0.005. That's going to be 2.58 if we go back to our table. And we said that S is equal to 0.1. All right. So now what we need to do is say, okay, we want a confidence level. Let's see here. Oh, we need to prescribe a width, which we didn't do. So we want a 99% confidence level, and we want that width to be plus or minus 0.012 ounces. So that's the kind of precision that we require here, because butter is expensive, all right? So we also have to prescribe that. So now what we're going to say is our z alpha over 2 times s over square root of n should equal this prescribed precision that we want of 0.012. So now we just need to rearrange and solve for n. So n is going to be equal to 0.012 over s over z alpha over 2. So n is equal to 0.012 all over 0.1 times our z, which is 2.58. And that should give us about, oh, we got to do a square, right? Sorry. And that should then give us an n of about 463. So that's a lot of sampling we need to do. We're going to have to take all those samples home and save some and give them to friends. So you can see very quickly, if you want higher precision, your sample size can go way up. That's all for our large sample confidence levels and interval lecture.